But this work is not with Eugene, but Saito-san here and Bahara-san, he's postdoc in Rick. I'm talking about many-body scalar state intrinsic to Floquet system. So we just upload it on archive. So let me start with kind of very preliminary. So first, let me explain energy eigenstate thermalization. So I'm basically interested in isolated quantum system. So in isolated quantum system in non-equilibrium phenomena, one of the important things is thermalization problem. So let me explain. So consider an isolated quantum system whose Hamiltonian H is non-integrable. Then energy eigenstate and energy eigenvector are written in this way. And roughly speaking, thermalization is like this. When a pure quantum state relaxes to a stationary state, and its thermodynamic property is described by statistical mechanics, we say the state is thermalized. So in order to explain that any initial state is eventually thermalized, energy eigenstate thermalization. So this is not very rigorous statement, rigorous definition, but this is basically of energy thermalization. Usually call it like just H. So the statement is as follows. Expectation value of any local observable equal to the value calculated by ensemble with the corresponding temperature. So we have to calculate. But anyway, this is energy eigenstate, and this is observable. When we calculate the expectation value in thermodynamic limit, value is very close to the average. This is basically the state. If we haven't heard of ETA, energy eigenstate thermalization, sounds very strong statement, but it indeed holds in general for Numerical system, and many people have numerically checked its validity. But there is, of course, always kind of counter example, and one of the very interesting example found with is called that model is called PXP model, and that state is called many bodies. Let me explain that. So PXP model is basically found or is found in the Berg Dhar state, found in this cold atom experiment. So this is laser, and we make tweezer like height. We put atoms inside, and we at excited state and ground state acts like rising spin. Excited like up spin and down. We can essentially make transverse field and longitudinal field. Double kill. And especially when H equal to 2J, there is a lot of degeneracy, and we are looking into highly degenerated part and doing perturbation with respect to gamma. Then effective Hamiltonian is written in this way. This P is projector to downspin. So if the spin has upspin next to that spin can't flip to upspin. Basically, this direction prohibits up-spin arrow. In that Hamiltonian, and starting with up-down Nail type state, they did quench experiment. And we see this type of persisting situation, so persisting for several periods observed. So it's slower, that relaxation is slower than thermalization. So it's interesting. But this, as you see, this oscillation getting smaller and smaller and eventually thermalized. But this is not the end of the story. Moreover, yeah, from this point, this is theoretical work, but it is numerically found that some energy eigenstate play model. So this is a result of numerical calculation. Each dot corresponds to energy eigenstate, and usually we see this dense band concentrated a lot of eigenstates. This vertical axis is entanglement entropy. You don't know the definition of entanglement, I will. But basically, this dense band is thermalized state band. But we see this 0, 1, 2, 3, 4, 5, 6, 7, probably 13 or 20 small number of very low entangled. So the authors claim that this is non-thermal state and yeah, very thing. So this is reminiscent of scarce state in else in single particle. This they claim potential of the scarce state to many bodies. So, but that many body scar is very new term. So let me clarify what I want to think about. What is many body scar? Basically, the system should be non-integrable. So for a given sector of conserved quantity, system should be non-integrable. Usually, non-thermal state appears in MBL system or integrable system, but these systems are characterized by conserved quantity. But in this system, so we divide vector, then we don't have global symmetry of the quantity. However, there is the states which violate each thermodynamically. This is the definition. At least our definition of. Then returning to numerical calculation, question is: are they very a non-thermal state in thermodynamic limit? Because their calculation is based on numerical calculation, like up to 24 sites or something. So we can't clearly see if it might eventually go to thermal state. However, the state at the middle are exactly described by the matrix for state. So we can answer this is non-thermal state. So let me explain that exact solution. This is done by Caltech group last year. So basically, basically the eigenstate, they gave the eigenstate four degenerated or one degenerated depending on boundary condition. The eigenstate at the middle of the spectrum. That eigenstate is between these four. This is matrix state. Matrix are like 2 to 3, so it's very. So thanks to their exact solution, we can safely say it violates because we can calculate magnetization and electricity. Magnetization is -1 over, and it's different from number. Entanglement entropy is log 2. It is independent of the size of the. So this is not volume rho. Real entanglement appears in the middle of the. So violation of the ETH is proven by the exact result. This is what I want to say now. So existence of the many-body scar state is confirmed. Then next first, so let me say a bit about Floquet system. So consider a quantum many-body system which is periodically driven. Floquet operator is basically time Hamiltonian is written in this way. So this is periodic, and for the period is capital T. Then Hamiltonian at time t plus capital T is time t. Then Floquet operator system is basically governed by Floquet operator. And state after the relaxation is described by Floquet quasi-energy eigenstate. Floquet eigenstate and Floquet quasi-energy are defined their way, Floquet operator. But in chaotic many-body system, when we drive a system periodically, usually energy flows into, so energy is in, temperature is increasing and a quantum state is eventually up to it. So ETH is likely to have to be replaced by another hypothesis called Floquet. But still we kind of hypothesize that state after relaxation should be. Statement is like this. Expectation value of any local observable is equal to the value with infinite temperature. So basically, there's no temperature. All the states become infinite. So, but this is basically a bad thing, I think, because everything, yeah, in infinite temperature, we don't have interesting phases. Basically, everything is ordered phases. So if we want to make something useful phases, we need to kind of fight against this Floquet. So let me summarize the introduction. So basically, quantum many-body scarce state. This is many-body scarce state by each end. Violation is confirmed by exact, but as eigenstate are Sagawa. Floquet system, basically, when the Floquet Hamiltonian is chaotic, then will eventually Floquet eigenstates are. So Floquet eigenstates are. So basically, we are not localized state. Do you mean by localized? At least we don't have any conserved quantity in the system. Basically, at least, yeah, I mean, basically, in this definition, we look at the system first. So first, we impose the system on integrable system. So the system shouldn't have local conserved quantity. The system has local conserved quantity, like MBS, then void. We don't have such conserved quantity, but the state itself is localized. In this definition, I think we state our state. Okay, right? Okay. So basically, so our work is basically we want to investigate quantum many-body scarce state in Floquet system. The question is, can many-body scarce state exist in Floquet system? And can we construct exact exception for Floquet scarce states? And can we just construction? And basically, all these questions are like yes. So yes, with good period and chain length, we can have scarce state. And can we construct exact expression? Yes, rigorous expression is identifiable. And we can also generalize. So let me explain the system. So our Floquet protocol is this BAM protocol. So we have H1 and H2, and from time 0 to T over 2, drive system H1. After that, H2 and returning, so alternate. H1 and H2, we use PXP, which is the same as people found scarce state. You know that, yeah, this is non-integrable Hamiltonian, and H1 and H2 are. However, different from stationary states, this Floquet operator depends on the period t. So Floquet quasi-energy and eigenstate should depend on the. So we first numerically perform brute force search with respect to t. Then this is what we found. So this is the period. This is some value of entanglement entropy. We use von Neumann entropy. So we prepare reduced density matrix, basically cut the system in half, and we test out of this subsystem A. And since we have exponentially large number of energy, Floquet energy eigenstate, we calculate all the entanglement entropy and plot the minimum value. It behaves like this. So we observe resonance-like behavior. So the period where this minimum entanglement entropy is not very small, we see this type of distribution. Here, this is basically Floquet. This is expectation value of px. So basically, energy of that Floquet state. This is energy, vertical axis entanglement entropy. Forget about this orange line. This is just reference. But we see all the states, essentially all the states concentrated to the maximum. However, at this resonant frequencies, we see at t equals 0, there is degeneracy. So there is four low entangled states are observed. By contrast, look at this red circle. All the states are concentrated to a very small entanglement window. So this is basically Floquet ETH holds except for these four states. So we want to and we show these low entanglement states are the Floquet states by showing exact solution. So let me first explain the exact result. The period turned out to be t equal to square root of 2 pi m. M is arbitrary positive integer. For this period, we always have four low entanglement eigenstates of the Floquet operator of the following form. Similar to Caltech group solution, this is written by matrix plus state. And alpha and beta takes 1 and 2, so combination, so there are four degenerated, not degenerated, four scarce states. Where the left half is described like this way, and right half is described. Schematically, it's like this. Left-hand side is state, right-hand side is this state. These two states are connected by down-down state. From this expression, you can readily see violates the Floquet because this state is a product of three states, phi 1 and phi 2 and down state. When I cut the state at the middle, there's no entanglement. So this immediately violates the Floquet. So next, we show the explicit construction why this is the eigenstate of that Floquet protocol. So, but in the construction, outlining of the derivation, we start with the exact solution in the time-independent system. It has four states. These states have energy 0, 0, square root 2, minus square root 2. we find that by superposing these two states, we can polarize the edge state. Like we superpose this way, right edge is polarized, so down, down. We superpose like this, by polarized, down, down. If superpose in this way, left edges are polarized. However, this superposition is a superposition of different energy eigenstate which have different energies. So this is not the eigenstate of original PXP. But the edge spin polarized with the period square root of 2 in our Floquet protocol. This is the difference. So in stationary state, they are not degenerated. But in Floquet protocol, we can make these states degenerated, essentially, the unitary case. So in this period, this states becomes the eigenstate of Floquet Hamiltonian. So we use this right edge spin polarized state as psi1 times this down down one. And we use left edge spin polarized state as right part psi down down times psi2. Then this is just a product of psi1 and down down 2. We can safely merge these three. State is our first state found in. So we again want to emphasize this is not the eigenstate of PXP Hamiltonian, eigenstate of the time. Once understand this mechanism, we can also propose some other protocol which has the similar state. I think this is more experimentally or realistic. This is general form, but this is very complicated. But basically, we are thinking about something like checkerboard like protocol. So we basically decompose sites into even blocks and odd blocks. And first, we drive odd blocks, and after that, we drive even blocks. Then we can still write down exact solution, exact Floquet square solution way. Both edge state are down state, but this state is matrix. In the limit, so simplest limit, like we drive 4 consecutive sites at the same time and 4 consecutive sites next to this site, the next protocol. Yeah, we think about this protocol. The Floquet eigenstate, our Floquet solution reduced to the product of down-down state and singlet state. This is singlet, this is down-down. This blue matrix product state part reduces that state. 2 sides blocks, then this blue part doesn't have anything, so it's just all down state. So basically, in the simplest limit, all down state is our size family. So I think these two simple cases are expected. So we do range and time equation. So basically, we are using these 2 sides block protocol. Then this yellow line is an all down state, Floquet square. Then we see it has oscillation, but in every period, it returns to the original position down state. So survives forever. By contrast, some random states like up down, next state, it behaves like this. At first, it has strong oscillation, but this oscillation immediately decays. And this value, this is time, and this is magnetic expectation value of magnetization at one side. It decays to this value, and this value agree with x value 1 over square. Basically, so our Floquet scar state is only the state which is in this Hubel space, but other states are immediately decay to state. Basically, other states satisfy. Is yeah. Result is obtained. That's why we other non-integrable system which I expect this type of, I think another way of kind of engineering state using Floquet system, because yeah, usually people use high energy expansion when we want to make states. We don't engineer Hamiltonian, but we stabilize some specific Floquet technique. Thank you so much.
Now session is open for questions or comments. Do you have any comments?
Why the name is SCAR?
Sorry?
Why the name is the SCAR state, SCAR? Speciality in this name?
Why we call it scar state?
No, name. SCAR, something speciality in this name?
Why it's called scar?
SCAR.
Oh, this is basically scar state is the state found in quantum chaos. Basically, in single particle program, they have scar state. They have some scar state. Like if we have some integrable model and we quantize it, then usually in quantum chaos we don't have real chaos because of uncertainty, but we still have some balance of wave function in trajectory. This is called scar, like years ago. And this is basically many body. They claim that this is basically many body version of scar. So
Other questions or comments? You have
Oh, can you please go back maybe one slide? No, one more.
sorry.
It's you presented the test of the Floquet scar state versus some kind of regular initial condition, and you showed that the regular initial condition sort of decayed to the infinite temperature state very quickly. Later, I think later. Yes. Your initial state is translational invariant state, right? So it's k wave vector equal to 0 irreducible representation, right, of the symmetry, and your Hamiltonians are also translational invariant, right? So essentially, my question is: have you compared your scar behavior with another initial condition, which would also be an irreducible representation of the translation symmetry group? Because in that case, you even for generic state, you would expect a much smaller number of basis states participating in anything and slower decay.
Basically, I took flux state as a
Say, for example, if you take up down initial condition, right? Would it decay?
up down.
Oh, but so that's not random. I mean, you
Sorry,
this blue thing you said it's a random spin up or down.
Sorry, I said it's kind of typical example, but I particularly specifically took up down.
So it's a concrete up down
this is
state.
up.
Yes. Okay. Thank you.
But still, yeah, of course. But if I also checked random product state, but basically the behavior is very similar. Or usually, if we take random initial vector, it decays much faster.
Are there any other questions or comments? You have comments? Okay, so if not, let's speak again.